62 miles an hour.
Sorry.
Dude, you guys can't
I don't. As soon as I upload them to YouTube, then I delete it.
We're going like that.
Like I knocked over.
Yeah, you can.
Yeah, he was
Okay, ready?
There are a lot of
Put those cell phones away, other things that might distract you. If you didn't finish last time's homework, don't do it right now because then you're going to be missing out on what you need to learn right now. Right? You can work on it later today. But all I said to you in front of you is your white packet, not the purple packet. Okay, so in order to understand endo and exo, we first need to talk about a certain type of graph that is used to show the energy transfer in a chemical reaction. So this right here is known as a reaction pathway graph. Now these graphs are graphs that some graphs you look at like whole picture wise. These ones really are a pathway. You really read them from left to right in how you look at it. So what it shows here, so label yours with me, okay? The starting line represents the energy of the reactants. So this is how much energy the reactants have before they do anything. Okay? Then, once they combine and start to react, for all reaction, there's always an uphill first because you have to start breaking bonds if you're going to make new bonds. And it takes energy to break a bond. So there's always a certain amount of energy that's needed for a reaction to go. Once you kind of reach this point, at that point, then it has enough energy to then just whoop, continue to products. So with all reaction pathways, you'll see an uphill and you'll see a downhill. But the difference is, in this case, this one has a much bigger uphill than it does downhill. Other reactions would have maybe a smaller uphill and a bigger downhill. And that's really our separation between endo and exothermic reactions. This peak right here is known as the activation energy. It's the minimum energy it takes to get it going, right? Like last time that Mason helped me out with the bubble one, right? Did it start while I was just holding it? No, he had to put a match to it. But then once he put the match, it then produced tons more energy after. So that would be an example of a small uphill and a huge downhill. Because I had to put a little energy in, I had to put a match in, but then the amount of flame that came out was way bigger than the amount of flame that went in. And that's how actually all combustions are, right? Any sort of burning, you just have to get it started and then it will go, right? It's the same way that your car works with your key, right? When you turn your key, it's causing a spark to ignite the gas. But once it's ignited, it's not like you have to continually keep igniting it, right? It just burns on itself. Okay? So that's kind of what we'll see as we look at these different graphs and things. So our first, if you didn't label the top peak, or at least draw an arrow so you know that the top is the activation energy. All right, so our first type is exothermic. Now, if it helps you to kind of remember, think EX, exiting. An exothermic reaction is where the heat is leaving the reaction, or it releases heat. Exothermic, exiting. Okay? The reaction that gives off or releases energy. So all exothermic graphs have a bigger downhill than they do uphill. Okay, so here's an example of one type of exothermic reaction or graph. Okay? Another way you can identify if something is exothermic is the products have less energy than the reactants do. Once again, because the products are lower than the reactants were, right? So exothermic, the products will always be lower than the reactants. Now what's interesting with identifying exo and endo, okay, if I were just to write an equation, this, there's no way by just looking at that whether it's endo or exo. Last time, you should be able to label what type of reaction could this be classified as though? Yeah, the synthesis, right? Two things becoming one. order to identify exo or endo, you need more data, particularly gathered from a lab setting, because energy is something that has to be measured. You can't just look at this and know what type of energy they have. So there's always going to be something more given to you when you're identifying endo or exo. One way is a graph. If they show you a graph, say, hey, this is the graph for this reaction, you should be able to claim, oh, that must be exothermic. Another way that you can do it is sometimes in a chemical reaction, they will write the energy in it. Put my example here, like this. So to help us understand whether it's endo or exo, they'll write the word energy in the actual problem. Where the energy is positioned tells you if it's endo or exo. Exothermic energy is always a product. So it's always going to be after the arrow, it's coming out. Yeah, so write that little example in that box there at the bottom. Okay, so one way you should be able to do it from a graph. Another way is if you see energy in the problem. The third way is it can just tell you actually the numerical value for the heat change. Okay, we represent that by the symbol of delta H. So this is the Greek symbol delta. It looks like a triangle, but it's called delta. And it is the symbol to represent change. So this means change in heat. Okay, if the change in heat is a negative value, so like for example for this one, it's like negative 250 kilojoules. If the heat is negative, that tells you the direction that it's going. Now it's important to recognize there's no such thing as negative heat, right? This is a change value. So think of heat like a bank account, okay? So if Cam's bank account is negative, which way is Cam's money going? Into his account or out of his account? Out. So negative heat means heat out. So if they give you, oh, the delta H is negative this, that tells you, oh, it must be exothermic because that heat is coming out of the system. Versus a positive value would mean it's going into the system. Okay, questions so far on endo or on exothermic? We're now going to talk about endothermic, but it's just completely opposites. The cool thing is, as long as you identify one pattern, you kind of know all the rest. Okay, so endothermic, once again, think of enter, exit, enter. Endothermic means the heat is entering the system. Okay, so this is where the reaction is absorbing the energy. It's taking it in. So our graph is always going to have the products higher than the reactants, right? So you're going to have a bigger uphill than you do downhill. Okay? The delta H would be a positive value, and the energy now is before the arrow. This is a case where energy is taken into the system. So we treat it as a reactant. Okay, questions so far? Okay, go to, in your homework packet now, it should be just the second page after the first one we did. I think it's called Endo-Exo Lab. Data sheet. Go to that page, and let's talk about our lab we're going to go do. gonna do 6 different reactions. 2 of them I'm gonna do as demonstrations, and then you'll do 4 with your lab group, okay? So I'm gonna do the first one in here to get us thinking, and then we'll head into the lab for the rest, okay? So the reaction I'm gonna do is number 1. I wasn't sure what order to put it. Okay, so demo number 1, which you'll put down here across number 1, okay? All right, so for this reaction, we are going to be mixing up a compound called barium hydroxide with ammonium chloride, and we're just going to pour them together and mix them up, okay? As part of this, because we're all about heat, we'll be using thermometers, right, to test whether the temperature is going up or down. One side note to these is they do have a cover on them, so you've got to take that off before you try to use them. It happens every year, someone just like sticks it in. I haven't checked the batteries, so if it is dead, let me know and I'll get you a new one. But otherwise, and they should be in Celsius, and that's what we actually want them to be in. I know, like in America, we typically read in Fahrenheit, but in science, we typically read in Celsius. So keep it in Celsius. Okay, so let me get our measurements out here. Okay. So I want you to kind of notice with your observations, like a little bit of like the before and the after, kind of like last time as well, to kind of see like what changes is it going through. Okay. So we're going to do 2 grams of this one. So this one's kind of like, it's white. I'll bring it around so you can get a closer look. It's really like flaky. It kind of looks like fake snow a little bit. All right. Okay. And then I'm going to add some of this, and then I'll just mix it together. Now, as part of the demonstration, I'm going to do it on this block of wood that I'm getting wet. Let's see why I've got. Okay, so let's get an initial temperature reading. It's probably just going to be whatever temperature the room is. So for initial temperature, put 23.5. Okay, hold on, sorry, let me grab one more cup. All right, this one looks more like salt or sugar. It's just a white thing though. It's very stuck together. Okay. Alright, so I'm going to pour them together. So here's what they look like, and then we'll just mix them. So same thing in the lab is you'll actually just use your thermometer to help you in, we're going to use it as our stirring device as well.
How long do you stir it for?
Good question, Cam. Probably just kind of watch the thermometer, and once you see it stops changing, like it's gone up and it's not going up anymore, or it's gone down and it's not going down anymore, then you know it's kind of done. So, I kind of know what this one should look like when it's done. Oh, and I can smell it when it starts reacting. It's quite a potent gas that it puts off. Okay, so I don't know if you can kind of see how it's looking, but it's looking quite different from how it did. And I'll bring it up closer so you can get a closer look. And then I'll let you feel, I'll tell you the temperature, but I'll let you feel, if you want to feel like the bottom of it, you can. So right now we're at -10 degrees.
So what's
Yes.
the point of the wood?
It didn't work as good as it should though, Lee. Because it's so cold, I should have gotten maybe wetter. It actually will freeze to the wood. Yeah, oh, there you go. Oh. I just had to push a little harder. Yeah, so the wood kind of just helps exaggerate how cold it is. I'll take it off though. You can see like the little ice. You see the ice ring? So I'll bring it around if you want to feel the bottom of it. Kind of get a closer look. So final temperature, I think let's put 10. It's not really going past that. So -10 Celsius is what you'll put for your final temperature. So then figure out what change in temperature it went through. Yeah, it's like surprising. Like, you don't expect just mixing like those two things together, right? That it would get like, yeah, it gets like really cold.
Is there packing
It's like a solid.
chemistry thing?
Say that again.
Is there purple packing in that?
Yeah, so you can grab that if you're grabbing.
You want to grab me one? Yep.
Wait, I can't wait. Is it like more like solid or liquid?
So yeah, it's now more liquidy. So this is one of the most bizarre things because you started in 2 solids. And then it turned to a liquid, but it got cold. Yeah, that's true. Oh yeah, we're in the bathroom.
Just ask for a new card to like is on that or something.
Okay, so when you calculate your change in temperature, it's always final minus initial. So when you're calculating a change, it's always the final minus initial. So your total change should be what, about 33.5 degrees change, right?
Rewrite -33 or
Down 5.
Yes, so -33. Okay, now let's talk about classifying this. So it felt cold, okay, endo or exo. Now, with endo and exo, the trickiest part is when students focus on the wrong system. Because the thing about heat is if something is releasing heat, well, something else in the universe is absorbing that heat, right? Because it's not ever destroyed. And if you focus on the wrong side of it, you're always going to answer these questions backwards. Meaning you're going to say it's exo, but it's actually endo. So when you think about a reaction, okay, you've got to focus on where is the heat going in terms of the reaction. Not for me, but for the reaction. So if I'm holding, oh, this is quite cool. If I'm holding something and it feels cold to my hands, what does that mean about the heat from my hands? And where's it going? So if the heat's going into the flask, what type of reaction is it? Endothermic, because the heat is going in. But if you think about your hands, you can always answer backwards because technically the heat is leaving your hands, right? But things that feel cold to us are because they're heat suckers and they're taking the heat from our hand. Does that make sense? Yep. Okay, any questions for now before we go do the lab? Okay, so the way, oh, that's stinky. Oh, if you're feeling sleepy, take a whiff of that. That'll wake you right up. Okay, so the way the lab is set up is so you guys are gonna do 4 different reactions. So I'm gonna do number 2 as a demo. I'll kind of get it set up, and then we'll do it maybe like while you guys are working. I'll pause you for a second. So you're doing 3, 4, 5, and 6. Okay, the reactions are up top, and then there's an instruction sheet that tells you what to do for each. They're pretty straightforward. Most of the time it's like mix these 2 things together, measure their temperature. Okay. The way it's set up though is it's somewhat of a rotation lab. So you're going to be at a station with your buddy, and then at your station you'll have 2 of the reactions that you'll do. And then you're going to switch with another group to do the other 2. It just saves me time from having to set up every station with all 4. So you'll kind of rotate a little bit. So we do need to wear lab goggles for this lab because some of these would be very painful if they got in your eyes, so we need to protect them. Safety-wise also, if you spill any of these on yourself, just run your hands under the water, but they can be irritating to your skin, so just rinse them off. Oh, I gotta move that. You not smell that yet? Oh, it's not. Once you're done with, I'll write on the board what the disposal is for each station. Some stations they're safe to go down the drain. Other stations we don't want them in our drains. So we need to put them in a waste beaker. So I'll kind of write that on the board which ones they are, okay? The only thing that got a little messed up is on the instruction sheet. For you guys, it's numbered 1, 2, 3, and 4, but on here, it's 3, 4, 5, 6. So if you want to write next to like the number 3 and just write 1, 2, 3, 4 off to the side, just to remind you when you're reading the instructions, which one it matches up with, so. Okay, do you guys remember what station you were at? It's been a little bit, but last time we did a lab, does everyone remember kind of their assigned station that they were at? If you don't, we'll figure it out when you come in there. So, okay, come grab some goggles and go to your station, and then we'll start distributing the chemicals. We can stop this now.
Smell that now, holy cow.
Did you get a whiff of it?